Hello, Isaac. Glad you can make it. Let me check you off here. Here's my Isaac. Hello, Alessandra and Felix and Kai. Hello, Aslan and Isaiah. Hello, Inessa. By the way, while we're gathering up, I'll show you what we're doing today. We're going to talk a little bit more about London dispersion forces and do some comparisons, and then continue on with another type of intermolecular force called dipole force. Dipole force. Okay, who else is here? Corsine is here. Aaron is here. Super. And Leo is here. Good. Yeah, we got about half of you. That's nice. Sina is checking in. Good. Thank you, Sina. Sure didn't miss anybody. There's Matthias and Cassidy. Super. There's Ethan. I gotcha. Yep, you're all set. Isabel, hello. Okay, got Isabella. Let's see who else is coming. Make sure we can see the screen now. I'll turn it so you can see that, because I'm not so important, but the screen certainly is, the whiteboard. I'll give everybody another minute or so, and then we're going to start up for the day. And I think we left off last time with CH4 and CH14. Okay. Spell I got. I need to know who Jamie O is, because I don't have a Jamie O, don't think. So Jamie O, tell me who you are. Devante, good. Glad you can make it today. All right. And again, I've got names. I don't know who you are. So identify yourself if you're from my class. If not, I will remove you. So Jamie O and Qwerty, both tell me who you are or you're gone. All right. That's the secret word. Bye-bye. Okay, but I've got Anton. And let's see. And I still got Jamie O. If you belong here, tell me who you are. Other than that, you're about to leave if I don't hear from you. Okay. Thank you. Isaiah, close. It's not butane. What is it if I got CH4? You might not be able to read it. It's only one C, so not four C's. Yeah, let's go ahead and start. Methane, good. Several of you got it. Okay, so I'm going to go ahead and begin. We'll let others come in late, but I don't want to wait for them. Okay, so recall from last time, Recall from good. Everybody's got that. Last time, this is what? A gas, and this is a liquid. Why? Why? What was the deal? They both have London dispersion forces, but what was the deal with hexane? Can you look back in your notes and see? Somebody type in a little answer. Why is this one a liquid? And that'll get to our first new thing today. The bonds are stronger? No. Bonds are all covalent single bonds. The bonds are identical. Remember, bonds are not what we're talking about. Bonds are between atoms. So this has nothing to do with bonds. They are stronger. I can't help you with they. I need a word, not they. Bonds, no, folks, look at these guys. They all are C's with bonds, single covalent bonds. It's the same bonds. The bonds are not the deal. It has nothing to do with the bonds. They're all the same. What does it have to do with? Okay, the London dispersion forces. Okay, so are stronger. For which one, Devante? Let's see if anybody else can write what that is in a nice sentence. Okay, so in the London dispersion forces are stronger. So the molecules attract and become okay, let's see if some of you kind of part of the answer there. Yes, good, Inessa. Good, Alessandra. Ding, ding, ding. We're going to come back to that. Yeah, and Sina. Okay, so it is indeed hexane. The London dispersion forces are stronger, so the molecules attract and become a liquid. Right? The molecules join together. Here's one hexane, here's another, and they join. And the reason from, Aslan, finish your sentence. Okay, the reason is what? Back to Sina and Alessandra. This guy, the molecules of hexane have more electrons, or we say a greater electron cloud. So a bigger cloud here and here means I can get more temporary dipoles, right? Temporary dipoles. So positive, negative, negative, positive. And for that instant, they pull a little closer, and they are stronger if there's more electrons. So we've got definitely more electrons, or we could say a greater size electron cloud. Let's have you guys apply that unless you got a question, okay? So this is, like I said, this prepare you for 10th grade topics, so it's a little more advanced, right? Okay, what we're going to ask you about are these two. You need a periodic table for this, don't you? So find your periodic table, and here we go. Cl2, Br2. Which is a gas, like at normal room temperature, which a liquid, and why? The big why question, right? So find Cl and Br on the right, but you got to tell which one is which, Leo. So find Cl and Br on your periodic table. And let's write a little sentence for an answer and punch it into me. So which one's a gas, which one's a liquid? And try and tell me why. Let's do green for a little bit. Let's see if we got some answers here. Just to check in, I still do not have, make sure here, I'm missing Jack, I'm missing Aaron, I'm missing Ayala, I'm missing Alicia, Hannah, and that's it. So if any of you are here, let me know, please. Because some of you, I don't know your email. Oh man, we're getting some crap out here. Okay, so Sherlock Holmes, identify yourself or you're out of here. And this is Baby Booey is out of here. I don't know who that is. Adios. I want only 9E. Okay, CO would be the acid. All right. I don't know what you mean by that. The question is not about acid, Isaiah. It's about which would be a gas and which would be a liquid. So neither would really be an acid. We're not talking about HCl. We're talking about Cl2. Okay, we get some other answers. Br is a liquid, Felix. Yeah, why? And Kai says Br would be a liquid because it has more electrons. Alessandra, Br is a liquid because the LDF is stronger. Also correct. Good. Let's have a look at that. So Br is bigger. It's got more electrons. So that means if I got a Br2 like this and another one, more electrons could be on one side for an instant than on the other. And so this would be negative, positive, and this would be, maybe I have the same thing happen here just for that moment. So this would be negative and positive. Compare that with Cl. Cl is smaller. So there's less electrons over here, okay? So I can make this side negative, but it's not going to be as negative because the electron cloud is smaller. And so even if I make the one next to it with opposite charges, you know what? It's just not going to be as much negative as this guy. So I'll draw them in blue. I got some London dispersion forces here, but here they're stronger. So those that said stronger London dispersion forces are also correct because of the greater number of electrons or the greater size electron cloud. I like that electron cloud idea because this is what you'll use in college. Whoops, sorry. Don't know what happened there. Now you can see. So stronger London dispersion forces due to greater electron cloud. Good. We're going to do one more and you'll see where we're going. Yes, exactly. Also right, Ethan. And yes, Anton, but now we got to ask why, okay? Cl is a gas because the London dispersion forces are weaker between the different Cl2 molecules. That's why it's on that side. Notice that side is sort of the upper ones. If I go down, Anton, I get to ones that are liquid and then solid as I go down because they got more electrons. Okay, let's do one more. All right, I'm dropping all my pens here. What about Cl, C, calcium tetrafluoride, CCl4 or CH4? Which is a liquid? Which is a liquid, okay? In other words, which will have stronger London dispersion forces? Which has more electrons? Which has a greater electron cloud? That's right, Alessandra and Ethan, you are right. So this puppy, why? Because Cl is bigger than H, so it's got more electrons, okay? Greater electron cloud to make these temporary dipoles, right? So this guy is a liquid, and the reason is exactly the same, isn't it? So between CCl4s, I get a stronger London dispersion force. So there's a CCl4 and another one, and somehow they're having opposite charges, so they're going to be a stronger London dispersion factor, okay? So it brings them closer together, right? And when they get closer together, they change from a gas far away to a liquid, right? So the attraction causes them to join up and become a liquid. It doesn't mean they're not moving, but it means they're moving by each other now. So they're in the liquid state instead of far apart like a gas, okay? Good. Here we go. Something new. Questions so far? And Ethan, it's not because the electron cloud is weak, it's smaller. We say the temporary dipoles would be weaker because there's less electrons, a smaller electron cloud. Okay, yeah? All right. Still looking one last time for the following: Jack, Aaron, Ayala, Alicia, Anna, and that's it. But now we're on to something else. Okay, so CCl is a liquid. So here's my question is, why would Br2 dissolve in carbon tetrafluoride, CCl4? Well, I want to draw that to talk about a little bit. Yes, Inessa, that's correct. So I want to draw that a little bit between Br2 and CCl4. Okay, turns out if I have a Br2 and it's in a whole beaker, remember both of these are liquids, okay? They're not aqueous, they're not in water, they're both liquids, so I can put these two together. Well, turns out if they have the same type of force, it means they dissolve well with each other. So let's look what happens. Let's pretend the electrons are here. So that side's more negative, this side more positive. And I can do the same thing here. Maybe this side's more negative, and just for that instant, this side's more positive. So even though these are different molecules, if they have the same type of force between them, they can attract each other and they then can mix easily, the two liquids. If they mix easily, we say they're soluble. Soluble. So there's my London dispersion forces. Okay, so why would Br2 dissolve in It both attract with London dispersion forces. I'm going to abbreviate that now. Abbreviate it because we've used it so often. So both attract with London dispersion forces. So can mix easily as liquids. And I'm going to give you a chemistry rule, okay? And here's the rule. It's like dissolves like. What that means is that if they have similar attractions within their own substance, then they will dissolve in another substance that has the same attractions. So like dissolves like. So, and since we're talking about dissolving, I'm going to talk about liquids, okay? So liquids with similar, well, and I'll just write that the same. Now I better write similar. You'll see why later. Same or similar intermolecular forces between the molecules. So liquids with same or similar intermolecular forces attract each other as well. And there's our good example, okay? So up here, Br2 and CCl4, okay? All right, and unless you identify who you are, you're out of here. So I'm going to get rid of you now, Jamie-O, unless you tell me your name in our class. I guess that's a no. Bye-bye. Okay, so any questions from you so far? We're going to look at the next type of intermolecular force now. So we've talked a lot about London dispersion forces. You're probably sick of them, but they're important, okay? So the more electrons there are, the stronger those forces are, and the more molecules come together and become either a liquid or even a solid like candle wax. Okay, then let's begin with something new today. How are we doing on time? We're doing okay. I want to remind you of something that you theoretically had in 8th grade. Let's do it in a new color for fun here. Let's do it in blue. Okay, if you make a baby periodic table, like this one up here, and if I go this direction towards F, I get increasing electronegativity. Who can tell me what electronegativity is? See if you can remember, or if you had it from me, I don't remember. And if you had an 8th grade, now you'll see what good it is, okay? So anybody remember, can you pull it out of your head, anybody? What is electronegativity? If you can't, it's okay. I just want to give you a chance. All right. Yeah, you're close, Inessa. Good. So electronegativity, it's how attracted a atom, really the nucleus, is to electrons. Generally, it's electrons in the next atom over. So what we say, it's the attraction of an atom to a pair of electrons in a bond. It turns out fluorine, it's small, but it really wants electrons. So F is the biggest electron pig on the chart. Fluorine really wants electrons, okay? Exactly, it's attraction to the nucleus, essentially. So if I got a fluorine, it has a lot of pulling power. So if I attach it to somebody else, let's say we attach it to somebody else, we're going to attach it to a big old Cl. But in spite of that, the electrons are pulled more this way. So, because F has more pull. I know Cl has more electrons, but it doesn't matter for electronegativity. The closer an atom is to fluorine, the more the pull is of the electrons towards whoever it is, in this case, F. Okay, so let's see what that means. Let's just write on the side. Electrons pulled towards F, because it's got a greater electronegativity. So what that means is this side of the molecule has more electrons there more of the time, permanently. It's not a temporary dipole. So this side is more negative, and this side is more positive. But this is not London dispersion forces. This is not just forming and then falling apart and forming and falling apart. This is a permanent situation. So what we say here is the molecule FCl has a permanent dipole. But you know what? Chemists just really say it has a dipole, okay? Or if you want to be really cool about it, you'll say that it has a dipole moment. That's what modern chemists call it. I don't quite know why that is. It sounds like it's having a bad day or a good day. I don't know. But they call it a dipole moment. So FCl has a very definite dipole moment. Well, what does that mean? Okay, check this out. I'm going to erase my little periodic table. Practically, what it means is these guys are like little magnets, but permanent magnets. So I got F bonded to a Cl, still a covalent bond. But this is always positive, and this side's always negative. And if I draw another one down here, FCl, and this side's negative and this side's positive, I better put those in little brackets, otherwise you don't know what the heck they are. So they're extra charges is what those are, okay? Then what we got here is an attraction between them. And that attraction is called a dipole-dipole attraction. So each of these has a dipole, a positive and a negative pole. So that's why they call it a dipole. So FCl molecules attract with dipole forces. Okay. That's a lot of dipoles. It really is. Imagine that you've got a box of magnets. Can you imagine that from when you played with magnets? Little bar magnets about this big. And I take the box and I shake them up. And if I shake them up, aren't all of the positives going to touch negatives and all the negatives going to touch positives? Okay, no, sorry. That's not magnets. Aren't the north poles and south poles going to touch each other in different magnets? Totally, right? That's what they do. You played with them. Opposite sides attract. So with magnets, we've got north, south is attracted to south, north. So this is not identical, but it's similar to dipole-dipole forces, okay? Your question also might be, does that mean they're stronger than London dispersion forces? And the answer is sometimes, and sometimes not. It depends on the situation. So let's write that. Dipole, dipole is sometimes stronger, sometimes weaker. Than London dispersion forces. You might say, Mr. Wise, that sounds kind of wimpy. Well, it is kind of wimpy because things really vary in chemistry. If I've got a lot of atoms in a molecule like candle wax, right? Or like octane or decane or something really big, there's a lot of electrons and the London dispersion forces can be pretty strong. If I got something tiny like methane, the London dispersion forces are pretty weak. Okay? So if I compare that to the strength of the forces between an FCl to another FCl, this might be stronger than methane between methanes, but it might be weaker than between like candle waxes. I don't know. I'd have to have some data, and I don't expect you to know. But now we're coming up to the biggie, okay? The really, really biggie. How are we doing on time? We're doing okay. Maybe I want one more example for you for dipole. Let me think about it a sec. Oh, let's do another one like this. How about let's do compare SO, it's a molecule, not a word, SO and ClBr. So we're going to compare SO and SPR in terms of intermolecular forces. By the way, can you have more than one intermolecular force? You can. You can. What's the math difference between London dispersion force and dipole-dipole? Or main difference. The main difference, Ethan, is for London dispersion forces, the little dipoles that form are temporary. They form and then disappear, form, disappear. For dipole, they're permanent. So like FCl, every one is permanent like a magnet. Whereas the excuse me, London dispersion forces are temporary. The dipoles form and then like don't form, and then because the electrons are moving all the time. But this one's permanent. Okay, let's take a look. All right, which one's closer? Which one's closer to fluorine? So which has more electronegativity? S or O? Which will pull the electrons more? Which will pull the electrons more? Who's closer to fluorine? Sulfur or oxygen? Look on your periodic table. Thank you, Anessa. Let's see if some other answers pop up from others. But she's right. All right, then let's just go ahead. Oh, there's a couple more. Yeah, oxygen. Thank you, Kai, Ethan, everybody. So here we go. What that means is this side's more negative. It's got, oh, sorry, I got to wrote the wrong charge. This side's more negative. It's got more poles of the electrons. So they spend more time over here. This side's more positive. And now, ClBr. Which one is closer to fluorine, Cl or Br? Look at this one now. Who's closer to fluorine, Cl or Br? Thank you, Kai. Good. A lot of you got it already. Cl. So here we go. Cl, and there it's attached to Br. Cl is more electronegative, so the electrons spend more time here, and this is more positive. They spend less time there. What that means is these guys like each other, so this will attract to this side, won't it? And that attraction right there between the S part of OS and the Cl part, the Cl part of ClBr, that's my dipole-dipole force. So you see how it's not a bond? It's between molecules, not between atoms. So it's between different, so there's an OS attracted to the ClBr. Dipole-dipole force. And I can even have the whole thing. Let's do another one down here. What if I have another one here, and I just flip that sucker around, so I say the S is here, and the O is here. And so now we know this side's more positive, this side's more negative. And lo and behold, I got lots of attraction between this one and this one here. Just like two magnets. So that's the same deal, isn't it? You know what I'm saying? How can one measure these forces? By comparisons, often in the lab, Ethan, by comparing chemicals and seeing visually if they mix. And then there are mathematical ways, once you get into it, to measure the amount of these forces as well. It's beyond what we can do in this class, but it can be measured. Good question. Okay, so what my point is here is that it's another example of like dissolves like. In other words, if these guys both have a dipole, dipole dissolves in dipole. They like each other. So we can say, aha, if they're liquids, again we have dipoles dissolve in dipoles. So in other words, like dissolves like. If things have similar intermolecular forces, they dissolve in each other. Like dissolves like. All righty. Good. Thanks for your participation. How are we doing? Okay, so why won't Br2, which is a liquid, dissolve in liquid fluorine chloride? Turns out they don't. So let's see if we can figure out why not. What are some common dipoles that are in everyday life? I'm going to answer that probably next time, Ethan, because I'm not quite that far. You'll see why. There's some really important ones. And yes, we will get to that. Thank you for asking. Okay, but for starters, we're going to start with stuff that's not in our everyday life. I know we don't have a lot of bromine or FCl sitting around, although this is often in stuff that is in your coolants, in your refrigerator, okay? Bromine, we don't have so much, which is good because it's a little too reactive for us. Can also hurt you. Okay, let's have a look at these guys. Well, the FCLs, we know what's happening, right? These guys got charges. And they're pretty strong dipole force, right? But the BR2s, let's do those another color. These suckers, the only thing they got is if they got temporary dipoles like this, and let's say like this, and like that. And so here, oh hell, I did it the wrong way, pardon me. They're not going to track. Well, actually, I can do it this way. So that'll track them to this one. So here we got what? London dispersion forces. But here we got dipole-dipole forces. Like dissolves like. So what that means is in a beaker, the BR2, by the way, is probably denser. Probably I'd get 2 layers of liquid. They don't mix. Okay, they don't mix. Why? Because like dissolves like. And so the BR2s, like other BR2s, because they do London dispersion forces in between them, if you missed that, and dipole-dipole forces like other dipole-dipole forces. So what I'm trying to say is we got a lot of FCLs down here. No, we don't. They'd be up on top. Sorry, I know that because BR2 is denser. So I got BRs down here, BR2s. But they're just not going to mix with these guys. Okay? So you'll have two layers. And frankly, it's because the molecules have different intermolecular attractions. That's the bottom line. So it's not like dissolving like. Different. Inter means between. Molecular, between molecules. Attractions. Let me tell you where we're going. Next time we're going to do the last type of intermolecular attraction. It's a really super strong version of dipole-dipole. And then we'll answer Ethan's question, where do we find this in real life? Turns out a lot of places. So why? Okay, hold on. Anton says, don't really get why they don't mix. What's really probably happening here, Anton, is in this case, the dipole-dipole forces here, they're stronger. In this one example. How do I know this? I know this because I've been in this business 30 years. So I'm not asking you to know that, Anton, but these forces are stronger, the dipole-dipole. So think of my magnets. I can't pull them apart because between the BR2s, in this case, the London dispersion forces are weaker between these guys than the dipole-dipole forces between the FCLs and FCLs. So Anton, you're going to not need to know that because you need to know more about the situation. But I'll tell you, if these are stronger, they stay together, and then these suckers are stuck, stay together, and they will in the liquid. They stay together, they don't really go across because these dipoles up here, they're only temporary. They're forming, disappearing, forming, disappearing. So it's not enough of a dipole, Anton, to attract F or Cl down here. These are much more attracted to their own kind. They like each other more than they like the Br2s. That's the best way to say it. So these guys, FCLs, like each other more, and the like is the attraction, okay, more than the Br2s. That's really what's it about, Anton and everybody else. It's a really good question, though. Thank you for asking. Okay, we'll see you next time. I don't know when I'll schedule. I got to look at my schedule, but I'll let you know. And thanks, everybody, for participating. Stay safe. We'll see you later in the week.